Hello everyone, and welcome to my presentation on r3d3, Optimized Query Compilation on GPUs. My name is Krolik, and I'm a PhD student at McGill University, supervised by Professor Clark Verbrugge and Professor Laurie Hendren. So efficient execution of data analytics is challenging, particularly with ever-expanding data. So data gets larger and larger by the day, but we still want our results quickly. Now luckily for us, paired with this challenge are two important observations. Firstly, query compilation is an effective strategy for repeated execution. So we're able to pre-compile a query, execute it multiple times, and amortize the cost. Secondly, we have the prevalence of accelerators, or GPUs, inside of most modern computers. And this is really the inspiration for our project r3d3, which is optimizing JIT compiler for processing relational database queries on the GPU. Now, numerous GPU databases have been proposed over the years, both in academia as well as in the commercial space, and typically follow the same approach, which is to implement database operations using GPU primitives and optimize each individual operation, typically in isolation. Now this works and it gives very nice results, but it has three important limitations. Number one, limited query support. So none of the above database systems are able to execute a comprehensive database benchmark set. They typically have problems with one or two queries. Number two, limited inter-operator optimization. So typically they optimize individual operations in isolation, not considering their impact on the overall query. And number three, slow compilation. So the compilation cost typically vastly exceeds that of the execution. So we attempt to address some of these limitations inside of our project with three main contributions. Number one, the optimized SQL query compilation targeting GPUs. So we're going to be able to automatically define GPU kernels given an arbitrary query. We have an optimized SQL library, which is going to be providing runtime support, and an improved compilation time. So really trying to improve the compilation time of the query to make it viable in runtime systems. We're also going to have the optimized runtime. This includes the data management as well as the JIT execution. And lastly, we're targeting coverage as well as performance. So we want to be able to execute the entirety of a database benchmark in addition to getting good performance over both CPU and GPU database systems. So the roadmap for today, start by giving a background on relational databases as well as GPUs, talk about the system design as well as evaluation, and lastly, finish with a conclusion. So a relational database is a database system used to store elements that are all interrelated. And they can be queried using SQL, which is declared a programming language specifically designed to query relational database systems. In terms of execution, we typically take the SQL query, convert it to relational algebra, optimize the graph to improve the performance, and to generate what's called a minimal cost execution plan. So the idea here is that we're going to specify for each individual operation what the most efficient algorithm is going to be. Once we have this, we can either run it inside of an interpreter or we can compile it before execution. Inside of this project, we're going to be marrying relational databases with GPUs, which is pictured over here from a high level. Now, I'm not going to go through the details of every single component, but I do want to point out two main parts. Number one, the execution engine. So on a CPU, we typically think about a single die with multiple cores, each operating independently. On a GPU, on the other hand, we have a hierarchy, which starts off with processing elements, which are equivalent to our cores, that work together in a multiprocessor. The multiprocessors are put together and to form the overall GPU. The same idea with memory, where we have a host memory on the CPU side, but on the GPU, there's three different layers. We have a registers page, which is memory private to each individual processing element, shared memory, which is private to a multiprocessor, and device memory, which is slower, but accessible to all. In terms of the compilation pipeline, NVIDIA GPU code, or kernels, is typically compiled in two stages. The first stage converting from CUDA, the high-level language that most programmers use, to PTX, where PTX is a machine-independent IR specifically designed for NVIDIA GPUs. This can be shipped onto users' computers, where it can be compiled down to SASS in a second stage, where this is a GPU family-dependent machine code used directly inside of the CUDA binaries. So next, I'm going to present the system design. And r3d3 is a complete GPU compiler as well as database system. And this means that it can both compile the input queries as well as execute and return the result to the user. It has three main parts: the automatic kernel definition, which is also called the GPU outliner, where we can define, given an arbitrary query, what are the kernels and what does CPU control go. We have the JIT compiler, which is able to convert from our high-level representation towards the code actually used on the GPU. And there's the execution engine, which is able to interpret the CPU host code, manage the data, as well as communicate with the GPU. Now notice the input language to this is not directly SQL. Instead, we're using a language called HorseIR, which is an array-based intermediate language designed specifically to represent SQL queries. And this has a few main advantages. Number one, array functions naturally expose data dependencies. So instead of having to perform a complex data dependence analysis to figure out how best to parallelize our program, we're able to naturally understand how it works from the primitive functions that were used. Secondly, array functions map nearly directly to GPU architectures. So instead of doing a complex mapping, we're able to do basically a one-to-one for most functions, and this makes it very easy to do. So as an example program over here, we have the following SEO query on the left, which selects the name field from a country table where some arbitrary size is greater than 10, and it would correspond to the following program inside of horse.ir. So we're able to load the table as well as the 2 column values, figure out those that are greater than 10, select only those that correspond to the appropriate mask, and form the output result. This is basically an imperative way of viewing the following SQL query. In terms of our target language, we're targeting PTX, which also stands for Parallel Thread Execution, and this is a low-level virtual machine and instruction set for parallel machines. And the advantages for doing this is firstly that it's machine independent, so we're able to target a wide variety of machines with our single compiler. It's scalable, which means that it's able to handle large amounts of data easily. And it's also optimized by the assembler. So if we first generate PTX, we can still feed it through NVIDIA's Stage 2 compiler to have good overall performance. This also allows us to reduce the compilation time because we're able to translate from a high-level code to PTX much faster than a more generic from CUDA. Now, remember what we're trying to do is convert from horsepower program down to PTX, and this first stage is going to be done using the GPU outliner. The GPU outliner is going to take in an arbitrary program, and it's going to determine what the GPU kernels are going to be. And we want to do this using 2 properties. Number 1, we want to maximize GPU utilization, and we also want to minimize intermediate data. The idea being that we want to keep data inside our registers as much as possible, eliminating the need to go to this global and also slower memory. So given this arbitrary program over here that we have on the left, with bold boxes indicating GPU-capable functions, as well as the asterisks indicating synchronization, we could decompose it into the following 2 kernels. The first performing the minimum reduction, and the second doing the actual compression. So we want to achieve this inside of arbitrary programs in our approach. And this has 3 main steps. So number 1, we have the shape and geometry analysis. The idea being that for some arbitrary program, we want to figure out how many threads are necessary and what their layout is going to be for every single operation. Given this, we can feed it into a compatibility analysis, which can determine what the kernels are going to be as a sequence of compatible operations, where a compatible operation is defined as those that can efficiently execute on the same geometry. And lastly, we have the outline builder. This is what's actually going to divide up the kernels and construct the CPU control code. Now, a bit more details of what the shape and geometry analysis are. A shape is going to abstract a data layout, which means that for every single data type inside our language, we're going to associate it with a corresponding shape. So we have this for vectors and lists, as well as SQL-specific types, so enumerations for foreign keys, dictionaries for grouping, as well as tables for the overall data structure. And these are going to be propagated according to shape rules throughout our program with a data flow analysis. Shapes are also going to be parameterized by sizes, which are going to give the exact dimensions of each part of the layout. So this can be constant or symbolic for things that we know statically, compressed for when we use Boolean masking or a subset of the data that's there, as well as runtime dynamics. So information that we can only know after running the program. Once we're given all this information, so we know for every single program variable what its shape's going to be, we can define the geometry of each step as well. So a geometry abstracts the thread layout for each operation given the operation as well as the input types and shapes. This can be fed to the compatibility analysis, where we're going to determine compatible operations that can execute efficiently on the same geometry. And this is trivially true for operations with identical thread layouts, but it's also true for those which are compressed. So the idea being that we execute a subset of the geometry for the steps of the program. And we divide compatibility up into 2 phases. The first phase is going to handle just data-dependent operations, as well as those that consider just identical geometries. So we can merge together identical geometries which are data-dependent on each other. The second phase is going to be able to handle 2 extra cases. Number 1, kernels which share input data. So if they're sibling kernels in the overall data dependence graph. And we're also going to allow compressed geometries to share the same kernel. So we're going to disable some of the threads and execute just a subset of them in subsequent steps. Once we're given our kernels, we want to generate the code. So for each horsepower function, we define an efficient PTX code generation pattern where we really focus on simplicity. So the idea being that we want to exploit parallelism and not do extensive optimization. The optimization can be provided by NVIDIA's assembler using their more detailed knowledge. And so we define patterns for unary and binary functions, so greater than, less than, plus, etc. We also have for reductions or aggregations in SQL stock. We have compression, same as selection, member, which can determine if an element is in another array, and we can also determine the unique or distinct elements. Once we have the programs, we can execute it inside the runtime, which is going to execute the query by interpreting the CPU control code and invoke the kernels. In addition to this, we have an SQL library, which provides complex functions with internal control flow, so sorting, grouping, and joining. We have an external library, which can provide complex math functions, as well as the CUDA runtime, which actually communicates and interacts directly with the GPU. Along with this, we have a data management because data management turns out to be a significant runtime cost. And so as part of our strategy, we define 3 principles for optimization. Number 1, we want to minimize the number of transfers. So we want to minimize the number of times that we're transferring data across the bus. Number 2, we want to minimize the number of allocations. So allocations are not free, and so we want to really improve the number of times that we're calling it. And number 3, we want to actually decrease the allocation cost because there is a minimum required for any particular program. And so our corresponding strategy has 3 parts to it as well. Number 1, we want to transfer buffers only on demand. So really keeping track of where data is stored and if it has been modified or not. Number 2, we want to try and compress or combine buffers as much as possible. And so this means that if we have multiple cells representing a single data item, instead of having 3 separate allocations, we have a single compressed buffer for the entire data structure, and we divide it up using a header to index into the structure. And lastly, to decrease the allocation costs, we're actually going to manage this ourselves by pre-allocating large pages and dividing it up as the runtime progresses. So we actually implemented the system and performed an evaluation by looking at the TPCH benchmark, which is a set of 22 queries commonly used for performance evaluation in the SQL space. And we tested this on a recent-ish bit of hardware, so Intel i7, as well as a 1080 Ti from NVIDIA. In terms of our comparison systems to see how we're performing against other runtime areas, we have on the GPU space, OmniSci as well as Blazing SQL. And on the CPU side, MongoDB and Horsepower, where Horsepower was the inspiration for our particular IR for this project. And they've all been updated recently, so they're active projects that are under maintenance. So the first thing to present is the execution breakdown, where for every single query, we want to show what the division or the stages are and how much time they take in the overall execution. So on the execution side, using the left scale over here, we have the overhead or the interpretive overhead of running our system, runtime analysis, data transfers is intermediate data transfer, as well as the final result, GPU and CPU execution, as well as the input data cache. So this is the input data or the tables which are stored in the database system. In terms of compilation, which uses the right scale over here, which is actually 3 times that of the left, we have the compilation time, which is our system converting from Horse AR down to PTX, and assemble corresponds to NVIDIA's second stage compiler. So the first thing to note is that we execute all 22 queries correctly. So every single one of them executes correctly on our system and returns the correct result. And number 2, nearly all the execution actually resides on the GPU. So with the exception of string operations, we actually perform the majority of the computation on the GPU directly. You'll also notice that data caching is very expensive. So for nearly all the queries over here, data caching represents over half of the overall execution cost. And so it really matters for GPU execution where we store input data. And lastly, compilation time dwarfs that of execution. So despite the fact that we're using this more optimized compilation pipeline, we still have a large cost by using the second stage compiler. So as future work, it would really be a good idea to address this second stage. So how does this compare against other systems? So firstly, we're going to look at the cache execution, which is the execution time excluding the cost of input data as well as the compilation phase. And pictured over here is a speedup graph indicating how we perform against the other 4 comparison points. Speedup indicating higher is better for our system, less than 1 indicates that we slow down. So observation out of this is firstly that the comparison GPU systems do not run all queries. So this is indicated by an X inside of the graph, where we have no support for the queries, which either means that they didn't run the query or they produced the incorrect result. Considering only the ones that did run, we have the following geometric speedups, which indicates that we actually perform better than all the other systems on both the GPU and CPU side in the cache scenario. Now, this is not true for individual queries, so some that don't perform as well, and it's typically due to either non-equality joints, so we don't support optimizing non-equality joints very well inside our system, and we also don't do extensive string manipulation on the GPU as it is right now. In terms of uncached execution, this concerns scenarios where you'd have the data changing on the GPU, but the query is going to be repeatedly run. This execution including input data costs, but excluding the compilation phase. This picture over here is again is a speedup graph, higher better for our system, lower is worse. And so firstly, we do still have a geometric speedup over all systems, although not as good in general, especially with regard to CPU systems which don't have to transfer any data. You'll notice that OmniSci actually slows down in comparison in this graph, and that's because it's optimized for multiple nodes, and it is not efficient on single node systems. So they've really considered GPU clusters as opposed to the individual consumer level GPU that we're thinking about inside of our system. Now, in terms of total execution, which is going to be end-to-end, including input data, execution, as well as the compilation cost, we still see speedup over compiled systems, but interpreted systems now perform much better overall. And so we're doing really well compared to other compiled systems where we have our optimized compilation pipeline, but it's still very slow compared to just running an interpreter because compilation often vastly exceeds that of the execution. So to conclude, we presented the design and implementation of an optimizing JIT compiler for processing SQL queries on the GPU. which means we have our optimized query compilation engine, the optimized runtime, including the data management and the execution, and we really target coverage as well as performance. Thank you.